Today, I'm going to go over op-amps. I'm going to go over op-amp behavior in general. This is important. It's ideal op-amp, operational amplifiers. This is a very important electronic component. And we'll use these to synthesize the functions. Last time we used negative feedback to synthesize basically a polynomial in the numerator and denominator. We did it in terms of block diagrams, but we didn't actually go ahead and show you all the things that are involved. But today it's important. So with operational amplifiers, let me make sure about this. Did everybody see the homework? If you looked at the homework, you should have had a lot of questions. Some of them you could do, a lot of them you couldn't. But this should answer it, hopefully. When you start with an operational amplifier, this is what it looks like. You'll have a negative and a positive terminal. And that represents thousands of transistors, many other things. There's power supplies that aren't shown. But the general rule is no current in. So I negative, I positive, both equals 0 volts, 0 amps. And the voltage difference here, V plus minus V minus, is 0 as well. So there's no voltage across those, no current into them. The way this happens is electronically it's forced to do this. Everybody with me, class? Now, with that in mind, we're going to start with the most basic circuits and then develop more. I'm going to try to take you through a couple of general problems and show you how this is used to really fabricate or synthesize all the stuff that we're talking about, the 1 over S and things like that. First one I talked to you about last time. This is a simple op-amp circuit. You have to know these, by the way. You're going to use this in your labs all the time. So this terminal is grounded, and this is the input voltage. Now, normally they don't show this terminal. It's assumed everything is measured with respect to ground. So if you see Vn plus, that's a voltage that's with respect to ground. Here, that's R1, this will be R2. We did this one last time. And what they really want is something called a voltage gain, AV. They want V out over Vn. This is a transfer function, if you think about it. Output over input voltage is a transfer function. It would be called our H of S. In this case, it's not a function of S. Are you right? Everybody with this? With me on this? Now remember last time, I asked you first what the current was through R1. I'm going to call this IR1. What was IR1 based on a loss? And how did you get it?
U over R1.
All right, now you're right, but I'm going to take it right through it. We look here and we know the voltage here is 0 volts, right? Therefore, the voltage here must be 0 volts as well. Correct, class? And therefore, the current flowing from positive to that 0 volt or negative terminal would be simply VI minus 0 over R1. So this is simply VI over R1. That should be obvious. Everybody got that? And this is the way you would do any other operational amplifier problem that you didn't already know how to do. Now, after that, these are ideal op-amps. The next thing you know, if that current IR1 flows this way, how much flows into the negative terminal? None, right? How does it happen? Magically. It's because of the design of the circuitry that controls this. It does not happen. It's forced not to happen. Where does all this current go? This way, right? So IR1 goes that way, right? If you didn't get it last time, watch. Make sure you do. Very, very, very important. Your laboratory work is going to be based heavily on this. How many have had labs with operational amplifiers? 1, 2. All right, you will, believe me. That means this voltage here, which we can call VR2, is simply going to be IR1 times R2. Correct, class? Everybody agree? I made sure I did the polarity this way. This is a typical mistake happens when I'm about to show you. Do you all see that, class? Maybe I should write a little larger. You got it? All right, now, what is this voltage plus to minus actually? Well, it's actually equal to what? VI times R2 over R1, isn't it? Because IR1 was VI divided by R1, correct? How many see this? Make sure. I'm sick right now today. I've had a heck of a fever, didn't get much sleep, and I hope you aren't, but you look a little tired. You look like I feel. Anyway, now, when I get that, this is usually where the problem comes in. I want the voltage here, V out here, with respect to the ground terminal. This is plus, this is minus. So the way you always get this from circuit analysis, you start at the negative terminal that you want the voltage across. And you come and you go to the positive terminal to get it. So I come from here to here, that's 0 volts, correct class? Go from here to here, still 0 volts, right? And then I see it goes from the plus to the minus, or a voltage drop of minus Vn or Vi over R2 minus R1. Everybody got that? Give me a show of hands if you see it. So it's minus V out right here is actually equal to minus Vi over R2 over R1. And therefore AV here, the voltage gain, output over input voltage, is equal to minus R2 over R1. Got it? Yes, sir.
How are you getting the minus numbers? You're starting from the ground at the positive terminal?
That's 0, no, at the negative terminal. You remember, you want the voltage from here to here. It would be what? It would be no difference here. This would be a voltage drop minus VR2, and then it would be plus V out equals 0, right? Or V out would be minus VR2.
Okay, so you're going into the op amp.
Sir, this is a voltage drop, right? It's plus to minus, correct? How many see this right? It's a voltage drop. This is called this is always called the inverting terminal. The input voltage polarity is inverted in the output. Now you can control the ratio of gain by simply the ratio of these resistors, R2 over R1. But it's always going to be negative. Got me on this? Now, something else I have to show you. This is general. We could use this if we wanted to get a simple amplification, but we get a negative factor in there. So one thing we can do is take this same circuit, and this is called an inverter, and just have a resistor here of R coming to the op amp, negative, positive. Another resistor R here, same exact value. This is V in, this is V out, right? Now those two resistors are equal, right? Y'all see that? What is V out going to be? It's just going to be minus V in, isn't it? How many see that? If the resistors are equal, right, then you basically get just minus V in as V out. So V in for V out for this one is minus V in. Everybody got that, class? How many see this right here? It's straightforward, but you must see it, you must understand it clearly. Don't be confused about this. Now, after that, the next thing I'm going to do is say, what if I want something where I just get an increase of, say I have an input voltage, I want it to increase by, say, 50, but I want it positive, all right? Listen to me now. Most of you probably see this. Well, I would just start and say this. I'm going to take a one operational amplifier here. I'm going to put a resistor here. I'm just going to make this R, whatever it is, make this 10 R, or 50 R, if I want to gain a 50 R. Now I know if this is V in, my V out here would be equal to minus 50 times V in. Do you agree with me, class? How many see this? Everybody with me? Now, I don't want that. I want a positive value. So now I go ahead and I say, I'm going to add a second stage. And it doesn't matter what the value of R is. It could be 10 ohms, it could be 100 ohms, as long as this is 50 times this. Now I go ahead and I put another one here. And here, I just use R and R. And now that voltage is inverted, or now my V out here is 50 times V in. You follow me on this, class? That's a way to use an inverter in series with a simple operational amplifier circuit to magnify the voltage without inverting it. Understand it? Yes, sir?
Could you also switch the terminals, like put the V in on the positive?
There's things you could do. You're thinking about, what if you fed this terminal, right?
Like, yeah, if you fed that, then.
We can go through permutations. What I'm trying to do is show you the most common and simplest ways of doing this, all right? We're gonna go through some, but right now I have to make sure everybody sees this part of it. Everybody understand this? Now what he just asked is, isn't there a way to do it with just one operational amplifier? The answer is yes, all right? I'm going to show you something. But this is common, and it's very common to tie that terminal to ground. And there's a lot of reasons for it that I don't have time to get into. When you get your, anybody here have analog electronics? When you get analog electronics, whoever teaches you will go into the reasons. Because this circuit itself is based on a ton of transistors. The first circuit right here, the input is called a differential amplifier. And I can't get into it now, I don't have a basis for me explaining it, but that's important to understand. There's a lot in there, a whole lot of stuff that I can't talk about. What we're worried about is the basic functionality of this. Now you can buy these things dirt cheap at any kind of electronics store online, Radio Shack, I don't think, is Radio Shack still around? No more. But what's an electronics store these days?
They don't have this.
So everything's online?
Mm-hmm. Yeah.
All right.
Well, at least not in Alabama.
I suppose these days everybody, they just jump online and get it from somewhere. Now I'm just going to talk about what he asked. We're going to do this together. Remember, there's a lot of ways to do this. There's not just one way. There's a lot of them. Yes, sir.
Can't you also do that same circuit with just 3 resistors?
Yes. And what you're doing is looking far ahead. And right now, what I need to do is just bring you one step at a time into and show you how this stuff works. All right? So work with me. The next thing we're going to do is feed the non-inverting terminal. Just work with me, all right? Now suppose I have this. I have an operational amplifier as such. But now I do this. Instead of grounding this one as such, suppose I put a resistor here, call it R1, and then ground this, or not ground, but let me do it this way. Put R1, R2, V out, and call this R3. And what I'm going to do is something, I'm actually going to do this just to start with the analysis to show you guys something. So if I have this, I want to do this one for a reason. So this is what I got, all right? And I have to do one other thing too. Call this, make this R4, make this R3, make this R1, make this R2. And go ahead, and I'm just going to ground this one. And there's a reason I'm doing it the way I'm doing it. What we want to do is find V out. I don't want to put a signal in yet. Now what we're going to do is analyze an operational circuit, an amplifier circuit with 4 resistors. But now our goal is just to find the output. There is no input voltage. Got me? All right, now work with me on this. We know that the voltage here is 0 volts, right? Are we in agreement with that? The next thing we also know is that no current flows this way. I there is 0, correct, class? No current flows in the plus terminal, correct? Now, what does that mean? That means that the current here, I'll just call it I1, or I1, is simply going to be V out over R1 plus R2. Take a look at that. Do you agree with that? Because R2 and R1 are in series, right? No current can flow in to the positive terminal. Do you all agree with me? All right. Now, with that in mind, we could have done with voltage division. I want to make sure you see it here. So what is the voltage across this resistor? I1 times R1, right? Or it's simple voltage division between the output and this plus terminal. Do you all see that? And I can say that this voltage right here at the plus terminal, V plus, would be V out here, and then it's going to be times quantity R1 over R2 plus R1, correct? Y'all with me on this? All right, what's the voltage on the negative terminal?
The same.
The same. So the voltage here is the same, and I'll just call it V plus, right? Now say again. Are you with me? Keep watching. Remember, I didn't put any values there. Now, if I know this is V plus, which is this, what is the current flowing here? And I'll call it I3. It would be this voltage divided by R3, right? V naught times R1 over R1 plus R2 over R3. And now that's that current, correct? How many see this? Right? We're just using the fundamental laws. No voltage across the inputs, no current input. We have a starting point. My starting point was the output voltage. You don't usually start there, but in some cases you do. Now I come here, and if I know that's the voltage there, what's the voltage here?
V plus minus V0.
It's going to be what?
VO minus V.
V out minus that. V out minus V plus, right? Well, matter of fact, let me do this. That volt, if I've got this current I3, I didn't say it right. This is I3 here as well, correct, class? You agree with me? Now, if that's I3, what's the voltage here? VR4 would be equal to I3, right, times R4. Do you agree with me, class? All right, now we're almost there. That means VR4 is equal to, and I'll go ahead and do it, I3 V out over R3 times R1 over R1 plus R2 here, all right? That's the actual current times R4. That's the voltage there. You agree with me? How many see this? So what's the output voltage V out? It's equal to what? The voltage increase here, right, which is this, plus the voltage increase here. Do you agree with me, class? How many see that? Y'all see it? I'm just saying it's the voltage increase here, plus the voltage increase here. Now, it's easy to get this. If we know I3, right, I put I3 here, that current flows through here and here. So what I can do is say V out here, the output voltage is going to be I3 times the combination of R4 plus R3, right? Or I can say it's I3, which is V out, right, over R3 times R1 over R1 plus R2 times R4 plus R3, and that is I think I got that right. Correct, class? And that's equal to V out. Are you with me? Now, I didn't put any voltage source in here. What you'll notice is the voltage V out cancels on both sides. And what you do is get ratios of resistors that will cause the circuit to actually operate. Now I'm going to do something a little bit different. Are you with me? I just did this one time to show you how you would go through an analysis with multiple resistors like that. All right, class? I didn't put any values for the resistors. All right? Work with me on the next one. If you didn't see this one, don't worry about it. I think it was actually not the best example. I should have got an actual value out. So now, the next thing I'm going to do is this. There's two things. This is negative, this is positive. Here, I'm going to go ahead and take this terminal And I'm going to take V out here, have a resistor here, R1, come back to here. I'll call this R2 actually. But this is R1. Ground it as such. Then I'm going to put a resistor ground it, that's 4. And then, actually this one's too easy. I'm just going to put V in here. Call that R5. Let me talk you through this one. This one, I almost made it too complicated. But I'll tell you what, I'm going to stop here because I'm thinking about some other things that are going to cause you. We don't need to get into this one yet. Let me do the next logical step before I go this route. We're not going to use this particular circuit. Let me go the way I had it planned. I'm sorry about that. Follow me on this one. Now what I'm going to do is this. This is minus, this is plus. Put a resistor here, R1, and then put a capacitor here, C, right here. This is going to be your output with respect to ground, plus to minus. Ground this. This is Vn, and ground it plus to minus. Now what I'm going to do is take a look at the input-output relationships for this one. And I'm going to do it two ways. I'm going to do it in the time domain, and I'm going to do it in the S domain. Are you with me? We're going to use the S domain primarily, but I want to do it both ways. When I take a look at this, I know this is VI of t here, by the way. It's a function of time. I know the current here, I1, is going to be equal to the input voltage as a function of time divided by R1. That I know for sure, right? Now I also know that that current is going to go up and this way. That will be I1 as well, correct, class? The next thing I have to know is the relationship between current and voltage in a capacitor. So I know that when I have a capacitor, and this is a current I of t, it develops a voltage V of t across it, and the relationship is C times dV of t dt is equal to I of t, right? Agree, class? Now what I'm about to show you is important. I is equal to C dV dt. How many know that? That's fundamental, you have to know. Now I want to get V. So V is going to be equal to 1 over C. Then I have to integrate I of t here, dt, and it has to be primed from 0 to t here, and that would be V of t. I'll call it Vc of t. And this is Ic of t. Do you all see that there, class? How many do? Now watch. Make sure you see this. That's the relationship between the voltage here, plus to minus Vc of t. I already have my I1 of t that's going into that capacity, don't I? Please take a look. Do you all see this, class? Right? I know what I is going to be. It's just V input, Vn, right here, divided by R1, isn't it? So I can stick, that current must flow this way, and I can stick that in here, and I can say that Vc of t is equal to 1 over c, the integral from 0 to t of that, which is Vn of t prime, dt prime, and instead of dividing by r and leaving it there, I put it out in front. So now I can say Vc of t is equal to the integral from 0 to t of V input of t prime dt prime. And therefore, when I look at the output voltage, I can see that V out of t with respect to ground is 1 over r times c, or 1 times c, times the integral from 0 to t of the input voltage, simply V in of t, dt prime. I did one thing that it's not quite right. What did I forget? Anyone?
Minus sign?
Ah, right, because it's actually a voltage drop, right? When you start at the ground, come up here, you get a voltage drop, so there'd be a minus sign there. And that would be the output voltage, right there, that would be associated with an input voltage here with a capacitor. Now that's a differential equation, and you can see what you've got there is an integrator. If I put a signal here, my output signal is the integration of the input signal with a factor of 1 over RC in front of it, right? If you made RC 1, then it would be simply the negative of the integral, and you could put a follower or an inverter after that and get the actual integration. This is called an integrator. Normally they don't show the simple inverter after. I mean, they do, but they don't talk about that. Are you with me, class? How many see that? That integrates the input voltage. You do or not? It's pretty obvious if you understand this part, right? If you understand that differential equation, then you can find the voltage across the capacitor. And if you understand that, you know the voltage has to be negative of that if measured at V out. Yes, sir?
So notice you keep labeling the positive and negative inputs to the op amp. Are they important in any way for anything that we're going to do?
They will be. And please just get used to putting the negative on top. It's called the inverting and the positive on the bottom.
All right.
You'll see in time. Yes, sir?
What would you do with an integrator? Like, why would you integrate?
Well, back when I was where you were, when we built computers, we didn't build digital computers. We built analog computers. This is a basic element of an analog computer. If you wanted to go ahead and do a differential integral equation, this would be the component used for integration. 1 time, 2 time, whatever. And it would be a real-time integrations or differentiation solution. Are you with me? I'm just going to do the differentiator next, and then it will go into the S domain, because that's really the important part. So that's an integration circuit, but in order to get it to work right, you would actually put another op amp with resistors of equal value in front of it, so you would get the negative effect canceled. Are you with me? But that's it. Now, the next thing is, what if I had this circuit? This is called a differentiator. Here I put my capacitor on the input terminal. This is Vn of t. And then I put a resistor here. That's R, and that's V out. Now, follow me on this. Remember, that voltage Vn is with respect to ground, right? The voltage here is 0, correct, class? The voltage here is 0. The voltage across this is Vn of t minus 0, right? Now you go ahead and say that, well, I know from here that C times dV dt is equal to IC of t, and therefore you go through it and you get this relationship yet again, right? That relationship holds. Now what you can say is this. When I look at this, the actual current here, I of t, is equal to C times dV input of t dt. Do you agree with me there? How many see this? That's the current, isn't it? Through that capacitor. That's the voltage. Take the time derivative of that voltage with respect to time derivative of that voltage and multiply it by C. It better be that current. Correct, class? Now that current can't flow into the negative. It has to flow this way. So now it flows this way, and that's I of t. Everybody agree with that? Now, what is this voltage going to be?
RC dV dt.
Well, call it VR, yeah. VR here is going to be equal to simply this current I times R. Or now it's going to be equal to R times C times dV in of t dt. How many see this? Right? Remember, we're starting with a basic understanding, no current into the operational input terminals, no voltage across it. Now, Finally, what's the output voltage in terms of that voltage, VR? How many see it's minus? Right? Because from here to here, that's a voltage drop. So that's equal to minus R times C times dVi dt. And that's called a differentiator, because think about it. If I make RC 1, I don't have to make it 1. But if I can get in coefficient there, make it 1, I take a derivative, always take a time derivative of the input voltage, right? And if I wanted to get a positive value of the time derivative, I just put another, I put an inverter in front of it. Do you all see that, class? So now we can do integration and differentiation. Finally, or the next thing is, now with operational amplifiers, I'm not going to work in the time domain. Usually when you do this kind of stuff, when you're building circuits to effectively simulate transfer functions for anything, the H of S. You work in the S domain, and there's never a cause for concern of initial conditions. So let me show you what I'm talking about. And here you're going to see the 1 over S business that we saw last time. It's going to be made clear. So now I'm going to show you the most general form in the S domain to do analysis, or impedance domain. Remember, we're going to assume that we have an input here, V in, right here, and we're going to have some input impedance. I'm going to draw a box here, call it Z1. And that goes into the inverting terminal. This is plus. Then it comes up here. All right, now Z1 and Z2 can be anything, but they're in the S domain. What was the impedance in the S domain of a capacitor, anyone? 1 over CS. What is the impedance of an inductor in the S domain? SL. That's right. And they can be any combination of those things. So now, my V output here, remember before it was minus R2 over R1 times Vn? Right? We could go through the analysis and say the current here is just Vn divided by Z1, because that's 0 and that's 0, right? Then we could take that current Vn divided by Z1, multiply it by that impedance, where I get Vn times Z2 over Z1, get this voltage, and then because I got a plus to minus, the output is minus that. Or you will get this, minus Vn times Z2 over Z1. Or the voltage gain is simply minus Z2 over Z1. Now we're going to talk about how you realize the 1 over S. Most of you by now probably see this. But you saw a lot of terms where there was 1 over S, right? When I drew those block diagrams, I had 1 over S, 1 over S. Some of you see it very easily, some of you don't. Now, what happens if I have this? I'm going to go ahead and put a resistor, R, simply R here, goes into the negative terminal of an op amp, that's positive. Then this is going to be 1 over CS, the impedance. And I want to know this output voltage. This is the input. Can everybody see this is simply Z2? 1 over CS. This is Z1R. How many see that? So even if you don't, you can always go through basic analysis. That's 0 volts, that's 0. Vn divided by R is the current there. That current all must go here. That current times 1 over CS is going to be the voltage there. But fundamentally you get what? Your output voltage is minus the input voltage times 1 over RCS. Or V out over V in the transfer function, AV is minus 1 over RCS, right? And if you wanted to do something where you wanted this value to be 1, remember we got a negative, we would make R times C equal to 1. Let me do it over here. And then what you'd end up doing is simply putting an inverter. Now, I'm going to show it to you right here so you can see this. And this should make sense to you. I'm going to do some problems, but I got to take you through this. So now if I take this and I have some R Vn, this is C, or 1 over CS, or SC here. Take that and then stick it through something that just has R here, both are the same. Now my output here, V out, will simply be equal to, or V out over V in, will simply be equal to 1 over S. Does everybody see that, class? How many see that? You remember that little box 1 over S? That's how you create that 1 over S box with an electronic component known as an operational amplifier, and a capacitor, and a couple of resistors. Understand, everyone? And that's, you're going to see in the book, he talks about that. Now, if we wanted to function S here instead, then you would switch these. The capacitor would be here and the R would be here. You would use a differentiator, not an integrator. Integration in the Laplace domain always, it leads to a 1 over S kind of feature. Differentiation always brings the S out linearly, as, all right, on top. Let's think about it. If x goes to x of t goes to x of s, derivative of x of t goes to s x of s minus the initial condition, right? If I take the integral of x of t dt, then I get a 1 over s times v of s, right? So keep that in mind. Finally, this is a couple things. This is how you realize simple poles. Now this one I want you to be attentive to. I'm thinking back about doing the positive terminal, but I think it would throw you off track because there's more to the actual mathematics. All right. So what about this? I'm going to call this R1, that's Vn. This is V out. The impedance of this is 1 over CS. The impedance of this will be R2, right? Now please follow me on what I'm doing. It's very, very important you're attentive here, because the book makes it a little harder, I think. I showed you something earlier where I said if you had a circuit and you just had some input Z1 impedance going to the negative terminal of an op amp, that's the positive, and then you had a Z2 that I said AV here was minus, or really just minus Z2 over Z1. And that's really like the transfer function. You can call that H of S. All right? It's a transfer function. It's a relationship, the input if it was X of t, the output if it was Y of t. Follow me, everyone? Show of hands here. How many with me? All right, now here, what is my Z1 for that? Right here, it's Z2 over Z1. Just use that formula. Over here, I have AV, right? That's minus Z2 over Z1 is V out over V in. All right, what is Z1? Take a look. It's just R1, isn't it? It's the value of the impedance between the input voltage and the negative terminal. So it's R1. Now what's this, Z2? You're used to multiplying first resistance times second divided by the sum of those, right? Don't do it that way. If you have two in parallel, say this parallel combination right here will be given as 1 over R2 plus 1 over CS, right? You follow me on that, class? Show of hands, how many see what I've done there? And if you had more elements, if you had another one in parallel, it would just be 1 over the third one, right? Now if I have that, this is my Z2, right? So I come here and I have quantity, I multiply this times that, or now I have 1 over R2 plus CS, and I have 1 over, and I can have R1 over R2 plus C times R1 times S. Y'all see here that I've just got it in a form where I have something that looks like I can get some constant over another constant plus S. How many see that? Now remember, for simple poles, you're always going to have something where you have A over S plus, say, I don't know, tau 1 here. The A is just an amplification factor. The tau 1 is the first pole, isn't it, class? Now here, if I factor out, divide top and bottom by CR1, then in fact I get this. I get 1 over CR1, and then I get 1 over S, and I get plus 1 over R2C. Y'all agree? Now take a look at this. How many see this right here? I'm not trying to move fast. Do y'all see what I've done there? I factored out, I've divided everything by CR1. I pulled that out in front. Got me? All right. So if I did this, I have to divide that by CR1, don't I? So I have 1 over R2C, right? Right? Plus S. Now why did I do it that way? This is an amplification factor. It's A. It's this. When you did your pole expansions, you solved for those, right? The partial fractions. What's tau right here? That's that, right? How many see that? Yeah, sure. So if you get a complex function and you want to implement it for simple poles, you can do it this way. I'm trying to show you some tricks and ways of using this. Now in your book, he gave you a bunch of problems where he wanted to implement it. He's talking about operational amplifiers, and I'll be frank about it. I threw that out there to make sure you took a shot at it, hopefully, so you realize what you didn't know, so hopefully I could answer your questions today. And then I showed you now how to implement the functional form where we had negative feedback. Remember, we had 2 functions? So with that in mind, now how about the homeworks? You don't like them? Which ones do you hate the most? We'll start. We'll do them. Let me just erase this first.
Can I just bring my laptop up to you, show you the circuit?
How bad of a circuit is it? What did they ask him for? Which one is it? Let's start there.
It's problem 4.31.
And is it a circuits problem?
Yes. Just the
And they-
op amp problem.
Oh, all right, help me out here. We can do it real quick. Let's do an op amp problem. That's negative, that's positive. Is this grounded?
It's through a voltage source.
Is it?
Through a
what?
voltage source and then ground.
There's a voltage source here?
Yes.
Yes.
Okay.
And then
Plus the minus and ground. Is that V1?
Yes.
V1 or VN?
Yes.
Okay, keep going.
And then through the negative, there's a resist R1 and C at the negative terminal of the
R1 and C, which way?
To the left.
on the left side.
Are they in parallel or series?
Series.
R1
Series.
and what?
Series.
So you got a resistor,
Yes.
R1 and C. Is this grounded?
Yes.
Okay, what's here?
R2.
Okay, this is not bad at all. And this here? And they want V out? All right, this is one you can probably see the answer for. Most of you understand this now. If this is the input voltage, right? Let's do this in the S domain, all right? Because that's the only way that makes sense. All right, we're going to do it in the Laplace domain. What's the impedance of this capacitor? 1 over CS, right? Now, I know you see it now. Work with me. If this voltage is Vn or V1, what's the voltage here? V1 as well, isn't it? There's no voltage difference between those terminals. How many see that? That's the key. Once you have that, game over. Now, if you've got Vn here, what's the current here?
Zero.
It's going to be Vn minus 0 divided by that impedance, isn't it? How many see this, right? The voltage difference between this terminal and ground, or just Vn, or V1, pardon me, V1, divided by this impedance is that current. How many see that? Right, so now I can say that I1 here, or I, is simply going to be equal to V1 divided by R1 plus 1 over CS. Do you agree with me, everyone? How many see this? Most of you, now you got it. You're not going to miss this one. Now, if I've got that current, what's the next thing I've got? I've got this current because no current goes into the negative terminal or the positive, right? If I have that current is I, what's this voltage? I times R2, isn't it, class?
Yes, sir.
Show them the fans. How many see this? Please give me some feedback here so I can tell. Do you see it or not? Because when I see people scrunching their eyes, it's like either my writing's terrible or I've not taught well. Now, if you have that, what is V out? You'll notice that's plus to minus. If I start here, I go up V1, right? Work with me. I start the negative terminal. I'll even draw it now. I start the negative terminal, start here, right? That's 0. Increase of V1. Do you agree? So right about the bat, I get V1. Now what else? From here to here, it's what?
It's an increase.
It's going to be an increase of I, or V1 over R1 plus CS times R2. So it's going to be plus V1 times R2 over R1 plus 1 over CS. Now, can you all see you can factor out the V1? How many can see that right there? How many see you can get output over input very easily now? Give me a show of hands if you can. How many do not see it? Who doesn't? Because I'll help you if you don't. You don't see it? All right. First, you guys see how I got this current, I. All right. You all agree that that I flows this way. You all agree this voltage is that I times R2. All right. If I want the voltage from here to here, I start at the negative terminal, right? Come here. This from ground to that point is V1, isn't it? Plus, what's the voltage from here to here? That's an increase. Isn't this an increase of I times R2? Pardon me? That's minus the plus. You went from lower to higher. And isn't I just V1 over R1 plus 1 over CS? Right? So isn't this it? How many see that? You can factor out the V1. You can get 1 plus R2 over R1 plus CS. That's fine. Doesn't matter. That says everything right there. Doesn't it, class? What did they want, actually? Whoever asked. All right. Well, if they want H of S is the transfer function. They want V out of S over V1 of S, and that's going to be simply what? 1 plus R2 over R1 plus 1 over CS, and that's the transfer function. Do you agree, class? You can cast that in other forms, but that's essentially it. Do you agree? What's next? What another question?
Well, they wanted H of T also.
That's the impulse response. Now, if this is, let's go ahead. If this is equal, listen now. If this is equal to your H of S, the impulse response is H of T, correct? So now we've got to put that in a form we can get an H of T. How would we do that? Well, how about I make this 1 plus, and then I'm going to multiply top and bottom by S here. So I have R2 over SR1 plus 1 over C. Everybody with me? I multiply top and bottom. Sorry.
Yeah, SR1.
S right there. SR2, right? By S. Correct, class? How many see this? Now I need the coefficient of that S right there to be 1, don't I, class? If I'm going to get in it. Are you with me? Show of hands here. Come on. All right. That means I simply pull out that 1 over R. So if I pull out the 1 over R1 term here, Now I get 1 over R1C here. And I get S there, don't I, class? Show of hands here. Now look, y'all agree I could take the R2 over R1, make it a constant? Show of hands. Agreed? So if I can make that a constant, I'm going to call A be equal to R2 over R1. And now I have 1 plus AS over, and it's going to be S plus 1 over R1C. That's my H of S. Now, listen, can't I expand this and get, well, actually I don't need to expand that anymore. I can get a single denominator if I want, but this will work too. What does 1 go back to the time domain as? Delta t, right? Now what about this one? I know what is 1 over, or forget A for a second. What is 1 over S plus, call it A.
E to the minus.
Yeah, it's going to be e to the minus 1 over R1 CT, right? But if there's an S in front of it, derivative with respect to time, correct, class? How many see that? I'm about out of time. I am out of time, but I'm trying to make sure. How many see that? Now, his book, does he show you this in the solutions I gave you? Yeah, he has to. He's got. Well, he may not do the circuit analysis, but you all see that, class? Give me a show of hands if you do. I'm trying my best here to try to make this simple. I'm not going to show you a lot of wild feedback loops or anything like that. What I'm going to do is give you some more problems with this. On Friday, we'll have a quiz based on simple operational amplifier behavior. All right? Nothing crazy. Basic. All right? What I used to love is students coming to me and saying, would you ask this? I don't know, I might. What about this? Oh, that sounds good. Do the homework, you'll be all right.
Oh, dude, you can make it.